Welcome to Pre-Calculus. Today we will investigate application of function composition to real-world scenarios, focusing on connections between algebraic representations and real-world measurements. We'll take a look at one scenario and then we'll apply function composition to answer a series of questions and then apply it to two different particular situations. So our real world scenario here occurs in a shoe store. So here's our scenario. A shoe store offers customers a 30% discount on the original price X of selected items. Then the store takes off an additional 15% at the cash register. Now what we want to do with that real world scenario is part A, write a discount function. We'll call this d of x that represents the price of an item after the first discount. So that's a 30% initial discount. So let's write that initial discount function first. So the way we'll do so is just by thinking about, in terms of buying a pair of shoes, how this discount price relates to the original price. So let's define the original price. We'll call that simply X. And that would be the price of a pair of shoes without any type of discount. It's the sticker price. Now, d of X for us is going to be the price of the shoe after the first discount. So that's a 30% discount. So once we've defined those two variables, I'm going to now write an algebraic rule to represent d of x in terms of x. So d of x in this case, if we think about it, it's going to be the initial price of the shoe minus that 30% discount. So the way I'm going to write that is 1x, so that's the original price. And then the 30% discount would be as a conversion to a decimal. So 30% as a decimal is going to be 0.33. I'm sorry, it's 0.30. And the discount would be that rate, 30% times the original price, which we're calling X. So that's a good discount function. What I can do is simplify that expression, 1x minus 0.30x. So there I'm really subtracting my coefficients. And what that gives me, 1 minus 0.3 is 0.7x. So to summarize here, the discount, which we're calling function d of x, equals 0.7x. And we'll box that. So that's the price of the shoe after the 30% discount. Now in part B, what we want to do differently is now write a price function that would be after both discounts. So P of d of x, notice that's a function composition. And what we want to represent with P of d of x is computation of the final price of the item after both discounts in terms of the original shoe price X. And we've already seen we're going to use function composition. We have a hint here. That's how we'll create this function P of d of x. So what we need to do again is pick up and define what will P of d of x look like, and then we'll make our composition to actually get a specific function. So again, we know d of x is 0.7x. That's what we just wrote in part A. So P of x, in fact, we'll call it P of d of x. And here I want to color code. So let me back up. So we'll call the final price in red there. And we're composing in d of x. So we'll write it in terms of d of x first, and then we'll substitute in our 0.7x. So that is really following the same pattern that we used for our first equation there. So it is the original price, which is after the first discount, so d of x, minus a 15% discount. So what I'll write 15% as, again, is as a decimal. So 15% is 0.15. You move the decimal 2 to the left of the price of the shoe after the first discount. So again, that's D of X. So you can kind of see generally how we're going to set that equation up. Now I want to make a substitution that includes, instead of simply that general D of X, specifically what we just wrote in part A, 0.7x. So this is now equals, substitute 0.7x for D of X minus 0.15 and substitute that 0.7x again. And that is in truth my composite function, the price of the shoes after both the 30% and the 15% discount. I want to simplify that. So one thing I can do here is notice that that really is 1 times 0.7x minus 0.15 times 0.7x. So there I can subtract 1 minus 0.15, that's 0.85 times 0.7x. And then to get a further simplification, I just need to multiply 0.85 times 0.7. So let's do that here on the side. We'll do our arithmetic here on the right. So we'll multiply really by 7, and then we'll find our decimal. 7 times 5 is 35. 8 times 7 is 56, plus 3 is 59. And I've got 3 decimal places, so that results in a product of 0.595x. And again, what's that equivalent to is P of D of X, that composite function that represents both the 30% and the 15% discount. So that is now representative of both discounts. So once I've got that final discount function written, so 0.595x, I want to apply it in 2 different ways. So my first application here in part C is just to say, what if I substituted a price of $50 in for X? And that's given here algebraically as P at D at 50. So let's calculate. So again, what I'll do is I'm going to write P, and now I'll just record all this. We'll color code to help it again. So D at specifically 50. And I'm going to pick up the equation we just wrote. So that's 0.595. And I'm substituting in the price of $50. And what I want to do then is multiply that out, see what that is, and then I need to interpret what's it mean in terms of this situation. So we'll multiply 0.595 times 50. 5 times 5, 25. 9 times 5, 45 plus 2 is 47. And 5 times 5, 25 plus 4 is 29. And then I'll bring the decimal 3 to the left. So in terms of price, that new price is $29.75. So I've arrived at a value. I do need to interpret and say, what's that mean in terms of the situation? So if the price that I was substituting in was $50 and it's coming out of the function at a lesser value, what we can say is that P of D of 50 is the final price of a pair of shoes costing $50 And what we're looking at here is after both discounts. So after both the 30% and the 15% discount. So we found the number, but then what we need to do automatically is turn around and find that connection between the algebraic representation and the measurements that we're seeing in the real world scenario. So I'm gonna circle that statement, because again, that's a meaningful statement in bringing together the number $29.75 and what's happening in the shoe store. Our last consideration is a different view. Now, what I want to do now is solve this equation, P of D of X equals 100. And similarly, I need to interpret the meaning once I solve that equation. So notice how this is different. In the previous question, I was substituting in $50. Here I'm saying the equation itself equals $100. So let's set this up algebraically. And again, that should help us as we go to try to figure out what is the connection between the algebra and the real life. So P, let me make sure I write this correctly. P of D of X equals, so I'm going to put the equation that we wrote in part B, that's 0.595 X, and we're saying that that equals 100. So our first step definitely is simply to solve that equation. So algebraically, what I need to do is divide by 0.595 on the left, and also divide by 0.595 on the right. So that cancels on the left, and we're going to get X equals some value. So what we should do is definitely calculate this. So I'm going to put 100 divided by 0.595. So recall, when you're doing long division with decimals, your first step is to reposition the decimal of that divisor. So I'm going to incorporate 3 more zeros in the dividend, and then note that that has moved the decimal over to the far right. So it's equivalent to 100,000 divided by 595. So let's calculate that. And I see that I've got the first place where I can divide in 595 is from 1,000. So it goes in once. So remember, long division, I multiply back. 1 times 595 is itself. And then I want to find the difference there. So 1,000 minus 595 is going to be 405. And then I'm going to carry down a 0. So now I need to make an estimate about what do I think 4,050 divided by 595 is as a whole number. So I'm going to just do some guessing over here on the side. Let's try 595 times 8. I'm just estimating what I think will be under 4050, but not too far under. So 8 times 5 is the 40. 9 times 8, 72, plus 4, 76. 8 times 5 again, 40. Plus 7 is 4760. So that's definitely an overestimate. Let's back down to 7. So 595 times 7. 7 times 5, 35. 9 times 7, 63, plus 9. Plus 3 is 9. Carry the 6 up. 5 times 7 is, again, 35. Plus 6, 41. So again, close, but too large of a multiplier there. So I think we're going to find success here with 595 times 6. So 6 times 5 is 30. 9 times 6, 54, plus 3 is 57. 6 times 5, 30, plus 5, 3, 5, 7, 0. And that's going to work for us. So I'm going to put a 7 here. And then multiply back, we just did that. That's 3,570. Subtract. And then carry some here. 15 minus 7 is the 8. 9 minus 5 is the 4. So we can see that 480 is lower than the divisor 595. So I'll carry the 0. And now I can use these values that I've multiplied on the side. So I see that 595 times 8 is 4760, which is just slightly less than 4,800. So that's going to go in 8 times. Subtract the 4760. 4,800 minus 4760 is 40. And then I'm working on my decimals now. And if I think in terms of the situation, those are my cents. Dollars are 178. Here I'm working on the cents. So I carry down the 0, and 400 is too small. So I'm going to put a 0 there for the 10th place. Multiply back, and that is really not much of a difference there. 400 minus 0 is 400. And then I'm going to carry down another 0. And then using my products here on the side, the one that will fit within 4,000 is 595 times 6, which is 3,570. And then 4,000 minus 3,570 is going to be 430. And to figure out if that's going to stay at 6 cents or round up to 7, I'll put a third decimal 0 there, carry it down. And again, if I look at my products there, I see that 595 times 7 will fit right under that. And that's going to be 4195. But I can end my division there. I see that it is going to keep going, but that allows me to round up to 179. I'm sorry, 178.07. So again, that solves the question. We use that division to solve this. So X in this case equals $178.07. So like we did with part C, here in part D, what I want to do is then interpret its meaning in terms of the situation. So if I was trying to solve for $100 and I was saying that was equal to P of D of X, well, remember P of D of X is, if we look back here, it is the final price of the item after both discounts. So when I calculate and get X as $178.07, that's not the discount price, that's the original price. So I'm going to write here on the side that this, what we have just calculated, is the original price. And let's specify and how it compares to 100. The original price that will result in a discounted price of $100 after both the 30% and the 15% discounts. In a way, it's the opposite direction. So in part C, what we found was the final price of a pair of shoes costing $50 after both the 30% and 15% discount. Here in part D, we're looking at the opposite situation. That $178.07 is the original price that will result in a price of $100 once I take the 2 discounts. Thanks for joining for this investigation of a real-world scenario that we apply function composition to make connections between the algebra and the real-world measurements. Thank you for joining. I'll let you make application of function composition to your own real world scenarios. See you soon.